I believe we've mentioned density at this point, but the book has a specific section on it, and so here you go. It doesn't really matter whether we are looking at things floating or sinking in water. Any fluid that we have, less dense stuff will float and more dense stuff will sink. If it happened to be the exact same density, it turns out you can get it to hover, what's called neutrally buoyant. Anywhere you place it, it will stay there. That's actually how submarines and fish work. It's not that they have the same density, it's that as they take on what's called ballast, as they pull in or push out water, they can adjust the density that they have and then either float or sink that way. The density is simply a ratio of mass to volume, and it is a property of all substances. It doesn't matter whether I have a copper penny or a copper pipe or a copper statue. Statue of Liberty was copper originally. Now it's a copper oxide coated copper, but it doesn't matter what size of it is. Obviously, they're all going to have different masses. They're all going to have different volumes, but the ratio of mass to volume is always going to be the same. And the formula for that is density is equal to mass divided by volume. Abbreviated, that is normally rho, which is the Greek letter lowercase r, and it is mass divided by volume. From algebra, we can then rearrange this. If you're given density, you can solve for either one of those, as long as just one of them is unknown. And you can also use density as a conversion factor, which we've looked at already. I will say that your textbook tends to go for the other abbreviation for density, which is just a capital D. I'll bounce back and forth between the two because I've been taught both. Just understand anytime you see that curvy P, it is density. As I mentioned already, things that are less dense will float on things that are more dense, and it really comes down to how closely packed together the molecules are. When you have high density, the stuff is packed together really closely. When you have lower density, the stuff is not packed as closely. There's more gaps in there, and it's that empty space that increases the volume. And by increasing the volume, since we're dividing by that, it's going to decrease the density. To be honest, rather than memorizing that, I always like to just make up numbers. If I have a mass of 1 and a volume of 1, then my density is 1. If I increase that volume, let's say I increase it to 2, well, now I have a mass of 1 and the density or a volume of 2, that gives me a density of 1/2, and so the volume has gone, or the density has gone down. It also turns out that as you heat up substances, because they expand, they will generally speaking become less dense, and so liquids tend to be less dense than their solids and will float on their solids, and gases are even less dense and usually will not only float but escape out. And I will point out that gas is a fluid, and so then it also is technically floating above. The atmosphere is floating above the solid and liquid parts of the Earth's surface. It is actually a density thing as to why we have those layers of the atmosphere and gases up above the surface. As I just said, liquids will tend to float on their solids. Water ice is actually an exception to that. Ice will tend to float on water. This seems really low for ice, how low it's floating. I don't know why it's quite like that. Ice tends to float a little bit higher in the water usually, but at this density, which honestly seems a hair low to me as well, it should be about 10% above the surface and about 90% below. That's not a perfect thing because it depends on a few other things, but what ends up happening is, because of something we'll learn about later in the year called hydrogen bonding, it actually causes the solid to expand a little bit, and so we'll get to that later in the year. But water ice floating on its liquid is actually rare. Most substances, the liquids will be above the solids. We've mentioned this already, but we can use grams per centimeter cubed or grams per milliliter. And of course, we could get rid of prefixes there, like grams per liter, or we could add prefixes onto the mass. I've certainly seen kilograms per liter before as a unit as well. These tend to be your solid and liquid ones, whereas this tends to be your gas one, but by no means is that always the case. And over here, we have some example densities. Pause if you want to take a look at them, but I'm just going to move right along. Since one of the goals in the long run for this course is to emphasize a lot of life science, it turns out that density shows up in bone mass and bone density in something like osteoporosis, which is generally happens in elderly people. And what happens is if you don't get enough calcium in your diet, then your body needs the calcium. It will get it from somewhere and it'll just go steal it from the bones. And so then it'll take it away from the bones and use it for the chemical processes that are going on in your body. And then that leaves you with porous bones. And although we talk about consuming calcium for strong teeth and bones, certainly that happens during growth. But later on in life, the increased calcium consumption, the purpose of that is to prevent your body from stealing that calcium from the bones. It's to prevent it from leaching it. And so it really doesn't increase the strength of your bones. Your body does not do a good job of repairing the bones. Instead, what it does is it maintains bone density and bone strength by providing the calcium your body needs for those other processes. So the end result's the same, that you have stronger teeth and bones, but it's actually not the calcium you're consuming that's going into those bones after you're done growing. You're no longer stealing from the bones and weakening the bones that way. Anyway, you can read the details on those two slides if you want. Moving on, when we have an awkwardly shaped object, it can be difficult to measure its volume. And so if you have something like a nice neat cube or some other nice geometric solid where you know the formula for figuring out volume, you can then measure your different sides, your length and your width and your height, and you can then calculate the volume that way. Or whether it is regularly shaped or irregularly shaped, something that you can do is measure volume by displacement. And so you have a known volume of water, like here they've got the 33.5 milliliters. You drop in your object, and when you do that, as long as it sinks, it's going to displace, it's going to move that volume of water, because now the new volume is the volume of your object and the volume of the water. Well, the volume of the object then is the difference between these two. And it turns out if you take physics, you'll find out that if it floats, that's not the case. It's not a way to measure the volume. You have to come up with other ways to measure the volume. But most objects sink in water, so that's not really an issue. And then, of course, you can weigh independently. It's best to do that before you drop it in the water, because then it's dry. Otherwise, you just have to make sure you dry it off completely. But you can weigh the mass of your object, and then you can use that to calculate the density. Of course, you don't have to do the volume by displacement like this. If you have a nice, neat substance like that, then you can just measure the volume, just put that into the denominator. But otherwise, this formula here works. Technically speaking, there's parentheses here because order of operations says we need to do this first, and so we got to put it inside parentheses for that. But here, with this volume change, we have a volume of 9.5 milliliters, and because those both go out to the 10th place, then we have 2 sig figs here also going out to the 10th place. The mass up here was 68.60. I kind of wrote over top of it there, but that's 4 sig figs. So our final answer is only going to have 2 sig figs. And when you punch that into the calculator, you'll find that its density is 7.2 grams per milliliter. That would also be the same as 7.2 grams per centimeter cubed, and since it's a solid, this tends to be the preferred unit for that, but that's not actually how you measured it. Technically speaking, you're converting from milliliters to centimeters cubed there, but that equality, when you have 7.2 grams per milliliter, the equality is that 1 milliliter is equal to 1 centimeter cubed. And so you really don't need to set up the problem here, because multiplying that number by 1, then dividing by 1, the only thing it does is changes the units, which is what gives you that one there. So then any amount of zinc that we have, the density is always going to come out to be that 7.2 grams per centimeter cubed. So doing this one on our own here, we are asked to calculate the density of a 48 gram sample of metal if the initial volume is 25.0 and the final volume is 33 milliliters. So a couple ways you can handle that one. One is to just kind of do the subtraction in your head. Two is, technically speaking, the formula for density with volume by displacement is delta V down here. That stands for change in volume, and changes in are always finals minus initials. The other way you can view it is it's just always the absolute value of your calculation. Then you don't have to remember which one comes first or second, and you have no negative numbers. But, of course, I think you can do 33 minus 25 in your head, or just know that this is what you need to do if you just look at this formula, that when I'm given two volumes that are the volumes of the liquid, and I'm interested in the volume of the solid, it's going to be a subtraction problem there on the bottom. So any one of those works, but here we go. It's 48 grams divided by 33 minus 25 milliliters. I will say that I like to do my units like this. Just saves me that little bit of extra writing from having to write milliliters twice. And it also kind of forces me to put the parentheses there to remember order of operations, to remember to do that on its own. And so that one there comes out to be 8. Of course, you could just punch this whole thing into a calculator, but then 48 divided by 8 is going to give me 6 grams per milliliter. However, this here, since we have the 0.0s, which I dropped when I did this, is really 8.0, which is 2 sig figs. And the numerator there has 3 sig figs, because again, I dropped the 0.0 there. So then our final answer has to have 2 sig figs. So even though this came out to be a nice neat number, I'm going to have to turn it into 0.60 grams per milliliter. And again, grams per centimeter cubed would also be acceptable. This one here basically says that we can use density as a conversion factor, which we've talked about previously, and frequently this is done to solve for an unknown mass. You can do it for an unknown volume as well, but let's just dive into doing one of these with an unknown mass. So an unknown liquid has a density of 1.32 grams per milliliter. What is the volume of a 14.7 gram sample? I'll point out that here it just said that we can solve for the mass. I mentioned that we could also solve for the volume, and that's actually what this one is having us do, is it's solving for the volume. So I'll show you both ways that you can do it. The conversion factor one is definitely much quicker. So like I said, I like to start with what I'm given with the known. Since you have two values here, I tend to prefer the one that has only one unit. Plus you could just kind of keep in the back of your mind that density is usually your conversion factor since you have those 2 units there. And as I've shown previously, it turns out it doesn't matter which one you start with. You can get there as long as you're careful with your units and make sure that they cancel out and you end up with the units that you're interested in, which, by the way, they tell us here, volume in milliliters. Of course, if you're not given that you want the volume in milliliters, you should still know that volumes are measured in liters, milliliters, meters cubed, or variations on those with other prefixes. And so anyway, 14.7 grams, and we need to get rid of grams, so I'm going to put grams on the bottom, and it turns out I can get straight to milliliters, so I'm going to put milliliters on top, and I'm going to use this as my conversion factor. So the 1.32 goes with the grams, and then I end up with a 1 here, and then our units are going to cancel out. Grams cancels with grams, we're left with milliliters, so I know I have it set up properly, and then when we do that division, I get 11.136 with the 3/6 part there, repeating milliliters. Well, we've got 3 sig figs here and 3 sig figs here, so our final answer needs 3 sig figs, so that's going to come out to be 11.1 milliliters. You can get the same thing using the density formula. It just takes some algebra rearranging. Density is equal to mass divided by volume. You know the density is 1.32 grams per milliliter. The mass is 14.7 grams per unknown volume, and so then at this point we have to do the algebra. Well, to get that alone, we have to multiply both sides by the volume here, and so we multiply by the volume there, and we multiply by the volume there, and that gives me 1.32 grams per milliliter times by volume is equal to 14.7 grams, and then I have to divide both sides by 1.32 grams per milliliter. 1.32 grams per milliliter. And so then the 1.32 grams per milliliter here cancel out. We're left with volume on this side. Over here on this side, the grams cancels with grams, and we have 1 over 1 over milliliters. There's no units here, so that's a 1 There's no units here, so that's a 1. And anytime we're dividing a fraction by a fraction, it's the same as flipping it, and so then that becomes milliliters in the numerator. So volume is equal to whatever 14.7 divided by 1.32 is, which you'll notice is the exact same thing that we did up here in a much shorter process. And so it's going to give us the same number. I'm going to go ahead and just round it directly with sig figs here, and then we are left with milliliters. Both methods will get you there. Obviously, the conversion factor is way fewer steps. So that is what I would recommend doing. So here's another one where we're going to use it as a conversion factor. If John took 2 teaspoons, that's a volume, that's an English volume, of course, of cough syrup that has a density of 1.2 grams per milliliter, and there are 5 milliliters in 1 teaspoon. Well, that sounds like a conversion factor. What is the mass in grams of the cough syrup? There is a way to solve this one using the density formula, but it ends up being a little bit ugly because you still have to do the conversion factor, and so it's much more straightforward, like I showed on the last problem, to just do the conversion factor. So that's what I'm going to start with here. Again, I'm given 3 different numbers, 4 if we count the 1 there, but one of those is obviously a conversion factor because this statement here tells us that those 2 things are equal. So that one there, we've got 2 volumes just measured in different units. That one's a conversion factor. Like I said, density is usually going to be a conversion factor, and this here is our other number. It's a single unit instead of a mix of units. I'm going to start with that, 2.0 teaspoons. So now we need to get rid of teaspoons, so we know teaspoons has to be in the denominator. Well, I've got teaspoons one other time in the problem, and it's this conversion factor that I put in the square brackets a moment ago, but that one there, which we also rewrote here. And so then we can put milliliters in the numerator, and then it is 5 milliliters per 1 teaspoon. And so now my teaspoons cancel out, and I'm not to a mass yet, so I need to get rid of my milliliters. And so that's going to be milliliters on the bottom, and I can get milliliters straight to grams using the density as a conversion factor here, so I'm going to put grams there, and then plug in my numbers. It's 1.20 grams per 1 milliliter. And so then my milliliters cancel out, and I'm left with grams for my units, which is what I want. So now let's just plug that into a calculator. 2 times 5 times 1.2, which is 12 grams. Coming through here and checking my sig figs, I have 2 there, 3 there, 2 there. This one here is exact. And so then we don't let that one limit us. And so it looks like 2 sig figs for the final answer, which is what we have already. There is another thing that is related to density. It's called specific gravity, and it's basically comparing the density of the object to the density of water. And we happen to use the density of water at a specific temperature there, but the density of water is always 1. And so essentially what happens is you have a density of the sample, which is going to be some number in grams per milliliter, and you're dividing it by 1. So the number's not really going to change, grams per milliliter. And really all it does is it cancels out the units, and you're just left with that number. It's a unitless number. And it works. It's always seemed a little nonsensical to me, and if we want to be really picky, the density of water isn't exactly 1, so it does change the number ever so slightly, but usually not within our level of significance. In the medical field, there's a lot of tests that we do to measure the specific gravity of this fluid or that fluid that's in the body. And for example, this one here shows a urine specific gravity test, which can be used to figure out how many things are dissolved in the water. One of the common ones is how much sugar is in the water, which then can be used to check kidney function or diabetes, etc. And another way to test sugar in the water, which is gross but used to be done in the medical profession, was just a dip and licked and see if it tasted sweet, which but I mean, before we had chemical tests, I suppose that worked. But what you could do is you could use a thing called a hydrometer, and the hydrometer is basically this bulb that has a weight at the bottom that is designed to sink, and then your scale actually reads back. You'll notice big numbers are low and smaller numbers are high, and if you had something like water, then it would sink to a particular level, but based off of the density, it causes this thing to float up higher, and as it floats up higher, then it gives us the reading a specific gravity on a scale. It can also be done with a dipstick, which a lot of times the dipsticks can be used to measure a lot of other things, and you can do a lot of other chemical tests, which tend to be pH or what other chemical components are dissolved in the water. Basically, the specific gravity isn't actually being measured there. What it's doing is it's measuring how many things are dissolved in there, and then essentially running the calculation that if this much stuff is dissolved in there, it's going to add this much mass, and adding this much mass then makes it this new level of density. Anyway, that finishes this section. As usual, there is a concept map here if you want to take a moment and kind of read it through there. But of course, be sure if you have any questions that you let me know.